Hi class! Today we'll be talking about complex zeros and also the fundamental theorem of algebra. On this page I have listed three functions, f of x, g of x, and h of x. And if you remember about factoring and how to approach these quadratics, we know that we can factor f of x fairly easily. X squared plus 7x plus 12 factors into x plus 3 and x plus 4. Each of these factors represents a real zero. X plus 3 represents the real zero of negative 3, and x plus 4 represents the real zero of negative 4. Each of these zeros is real and also rational, and we could have found them using the rational zeros theorem. For g of x, we have a little bit more complicated looking function, x squared minus 4x plus 2. It is not factorable, so we use the quadratic formula to find our x values. And notice how I factored g of x using each of these factors in an x minus 2 plus radical 2 and x minus 2 minus radical 2. And so it is written in factored form, but these are not rational zeros. These are strictly real zeros. And then we have h of x, which is x squared plus 1, which if I asked you to factor it before, we would probably accept the answer that it's an irreducible prime. It does not factor. Let's see what happens when I use the quadratic formula on that. So using the quadratic formula yields the result that x is equal to plus or minus I, meaning that I can factor h of x to be x plus I and x minus I. Notice that each of these factors is not real. Now my f of x has rational zeros, which are also real zeros, which are also complex zeros. In fact, all of the zeros on this page are complex zeros, but only the zeros for f of x and g of x are real as well as complex zeros. But the factors for h of x are the only ones that are complex without being real, and we call that strictly complex. In this section, even though we are talking about complex zeros, we are talking about all of the zeros, not just the complex, strictly complex ones, but the rational and the real irrational and the strictly complex zeros. All of those are covered under complex zeros. Now if you recall our complex number system, we started off with natural numbers like 1, 2, and 3. We moved on to whole numbers, which is basically 1, 2, and 3, and including the 0. And then when you learned about negative numbers, we called all of them integers. So we'd go from negative 3, negative 2, negative 1 to 0, 1, 2, and 3. Then we learned rational numbers. And rational numbers aren't just fractions, but they're anything that can be written as a fraction. So 0 is a rational number because it can be written as 0 over 1. All the natural numbers are rationals, all the integers are rationals as well. But we also have irrational numbers like radical 2 or radical 3 or pi or e, and all of these numbers cannot be written as fractions, fractions using integers. We have the irrational numbers, which are all the numbers that are not rational numbers. And all of these numbers that I just listed are part of the real number system. And all of those here, and even combinations of them, can be used as real numbers. So I could have something like 2 plus radical 3, which combines our rational numbers with our irrational numbers. Now all of these numbers that I've said, even though I'm saying real numbers and rational numbers, some numbers fall into both categories. So while we were looking for our real numbers, or while we were looking for our real zeros, we first had a rational zeros theorem, found only the real zeros which also happen to be rational numbers. But there also could be real zeros which are not rational, and those are like the ones that we found for g of x. And then, like we saw with that last example for h of x, that had an imaginary number in it. And so those are part of complex numbers. Complex numbers are any combination of real numbers and imaginary numbers, including just the real numbers themselves. All real numbers are complex numbers, even if there is no imaginary I in it. But when there is an imaginary number I, then we have to call them complex numbers. They cannot be called real numbers. So something like 3 plus I would be complex, It combines our real numbers with our imaginary number to make a complex number, a strictly complex number. But, like I said, all of our real numbers are complex numbers too. They're real numbers with their imaginary coefficient is 0. So we have to keep that in mind. So looking at f of x, it's an nth degree polynomial, and with our coefficients, all of our a coefficients will be complex coefficients. Now, we say that r is a complex 0 if, when you plug r into the function, it yields 0 as an answer. So f of r is equal to 0. The theorem that we have about this function is that if it's complex and we allow for complex zeros, then we know that this can be factored into linear factors. By that I mean all of the powers on our factor are x to the 1. They're all very simple linear factors with n amount of roots. There's an n amount of roots because each of these roots is going to be a complex number. And so I can write this, no matter what degree it is, there will be that number of roots if I'm allowing us to have complex numbers as our roots. Now this wasn't necessarily true when we were looking at real zeros. Even as we saw in the previous example, f of x was degree 2 polynomial and it had 2 real roots. G of x was a degree 2 polynomial and had 2 real roots. But h of x was a degree 2 polynomial, but it had no real roots. And so whenever we talked about real roots, we said, well, the real roots, it could match the degree, but it could have less roots than it had degree. But if we're talking about complex roots, and if we allow for complex roots, then we say the number of complex roots always matches what the degree is. They will always be the same. So if it's an nth degree polynomial, you will have n number of roots.
Just to reiterate a few theorems that were in this section and the previous section, if you have a 4th degree polynomial, then you can have up to 4 real zeros. Notice in our example, we only had 2 real zeros. We had 2 linear factors and 1 irreducible quadratic factor. But likewise, if we're allowing ourselves to have complex zeros, then for this exact same 4th degree polynomial, we will have exactly 4 complex zeros, where 2 of those complex zeros are complex and real, but 2 of those complex zeros are strictly complex, not real. And so we can take that irreducible quadratic and break it down into smaller linear factors if we allow some of those coefficients or some of those constants to be imaginary or strictly complex. We have the conjugate pairs theorem, which basically says that if you have a polynomial and the coefficients are real numbers, and you have a complex zero of the polynomial known as r, which is a plus bi, then we know that the complex conjugate r bar, which would be known as a minus bi, is also a complex zero. We know this to be true because if the coefficients are real numbers, it cannot have any imaginary portions to it. And if there's any imaginary portions to our roots, they have to multiply with a complex conjugate so that they cancel out with each other. Let's see how that works. If I had a polynomial and it was just x plus I times x plus 2, when I multiply it out, you would see that I have 2 terms which are real, and then I would have 2 terms which are complex, and complex not real, because actually all 4 terms are complex. But we have those imaginary portions to it, and those would not be real coefficients. But if I have this other polynomial, x plus I and x minus I, and I multiply it out, because I'm multiplying conjugates, those 2 middle terms will cancel out, and the I squareds will turn into a real number. Multiplying by the complex conjugates, when you have roots that are complex conjugates of each other, they will all of their imaginary terms will always cancel out, and you'll be left with only the real portions. Let's do one more example. If I have the complex 0, 2 plus I, then I will have also the complex conjugate of that 0, 2 minus I. And so if I wanted to write this in factor form, I have to do x minus r and x minus r bar. Keep in mind that your factors are always going to be x minus the complex zero. It's always going to be in this format, x minus. So then we're going to simplify that. That's going to be x minus 2 minus I and x minus 2 plus I. And you can multiply it out by just multiplying all three terms by all three terms. So if I multiply all three terms by all three terms, I should get 9 terms. But when I add them together, I would get x squared minus 4x. The plus ix and the minus ix should cancel out. I get plus 4. The negative 2i and the plus 2i will cancel out. And then also get minus negative 1. So I get x squared minus 4x plus 5. And so I had I had complex real zeros, but when you multiply them out and they have complex conjugates, all of those imaginary portions will cancel out if you do it properly, and you will be left with only real number coefficients. Let's use the conjugate pairs theorem to solve question number 1. The question asks us to find the remaining zeros of f of x whose coefficients are real numbers. So there's your first clue. We had to make sure that the polynomial we're looking for has coefficients which are real numbers in order for us to be able to use this theorem. And then it says that the degree of the polynomial is 4. So that tells me I'm looking for exactly 4 complex zeros. And now we're given 2 of the zeros, and they're both complex. And so if we know 2 of the zeros and they're both complex, then we also know that their complex conjugates are also zeros. And so I would get 2 plus I, and I would get plus I. These are really 0 minus I and 0 plus I. And so there we go. And those are our 4 zeros. If I wanted to set them up in factored form, I would say x minus 2 minus I, x minus 2 plus I, x minus negative I, and x minus positive I. And so if I wanted to simplify this, I would get x minus 2 plus I, and x minus 2 minus I, then x plus I, and then x minus I. If you want to find the polynomial, you would multiply this out. And by multiplying it out, I would get x squared minus 4x plus 5. And over here, I would have x squared plus 1. Multiplying all 3 terms by all 2 terms, I should get 6 terms. And simplifying, I would get x to the 4th minus 4x cubed plus 6x squared minus 4x plus 5. I went a little bit fast through this because we just practiced this one. And so we should already know from our previous work that it was x squared minus 4x plus 5. And so I was able just to work through that quickly. But notice that I have a polynomial of 4th degree. I had 4 complex zeros in it. And when I multiply them out, I end up with all real number coefficients. No imaginary coefficients. And so there you go. We solved question number 1. For question number 2, we're asked to form a polynomial with real coefficients having degree 5. And it gives us sum of the zeros. And we have to come up with the other zeros. So it says we have a 0, which is 1, multiplicity 3. So that actually means we have the 0 3 times. So we have x minus 1 to the 3rd power. And then we have the complex 0. So that's going to be x minus 1 plus I. And because of the conjugate pairs theorem, we know we have the complex conjugate, which is going to be 1 minus I. Let me just put that here. That's what we know the other 0 to be. And so if we multiply this out, we will have a 5th degree polynomial, because you have 3 x's here and then you have 2 more x's. And so when you multiply that out, we'll have x to the 5th. Let's go ahead. You have to be very careful when you write your factors. There's a lot of confusion for students when they take their factors, which have 2 terms in them, and they write them here. And always our factors are always going to be in the form x minus r. So whatever the r is, you go x minus that r. And so let's just simplify this once. Say x minus 1 to the 3rd. This would be x minus 1 minus I, and x minus 1 plus I. Let's go ahead and multiply that part out first. Let's get rid of those imaginary coefficients. I'm going to get x squared minus x plus ix minus x plus 1 minus I minus ix plus I minus I squared. Now be very careful when you multiply that out, that my x terms do not cancel out. But my I terms do. I have ix and negative ix. I have negative I and plus I. Those do cancel out. And so I'm going to get x minus 1 cubed. And this one simplifies to x squared minus 2x. And I have a plus 1. And this one's going to become a plus 1 because that's minus a negative 1. So that's going to be plus 2. And so then we need to multiply this out. And just rewriting it as x minus 1 to the 3rd power so that I can multiply everything out. Make sure you do it properly, or you're going to do all this work and get the wrong term. Make sure when you multiply a 3-term polynomial by a 2-term polynomial, you should get 6 terms before you combine them. And then if I have 4 terms times 3 terms, I should get 12 before they get combined. And when I multiply it out, I like to stack my terms just so it's easier to add them together. And there you go. We have our 5th degree polynomial. It had 5 zeros, 3 of them complex real, and 2 of them strictly complex, so they were complex conjugates. When we multiply them out, we get a 5th degree polynomial. We know that we should call it f of x because that's what the question tells us, and so that is our answer. Question 3, similar to question 2. We have a 4th degree polynomial. We want to find all 4 zeros. We're only given one of them this time. But it is complex, and we have to look at our polynomial. It has all real coefficients, so therefore I can apply the conjugate pairs theorem, and I know that since one of my zeros is 3i, the other 0 is negative 3i. And so let's go ahead and multiply that out first. Let's come up with our factors. Our factors are going to be x minus 3i, and the other one's going to be x minus negative 3i. And we see these as conjugates, so we should be able to say x squared minus 9i squared, which turns into x squared plus 9. So what we're going to do is, like our previous section, we have a factor. We're going to divide our polynomial by this factor, and then we're going to see what is the reduced polynomial and see if we can factor that. Now, the thing is that x squared plus 9 is not a linear factor, so we can't use synthetic division. So we're going to have to do polynomial long division. H of x, as in its factors, we have x squared plus 9, and we have 3x squared plus 5x minus 2. And we have multiple methods that we've learned about how to factor
quadratics, so you can refer to any of those methods that you want. I'm just going to do factor by guess and check. So I get x squared plus 9, and I think one of my factors is going to be 3x, the other one's going to be x, and I have 2 and 1. No, that's not right. 2 and 1, and I have this one. Now that means that they multiply out to make negative 2, but then this would make positive 6, and negative 5 would make my middle term 5x. So there we go. Alright, what are the remaining zeros of the function? I'm going to go ahead and erase my long division work so that I can list all the zeros of the function. They did give us one of the zeros was 3i. The other one, based off of the conjugate property, we know that we'd have negative 3i. Then those two made up our first irreducible quadratic. Then based off of 3x minus 1 as one of our factors, you can set it equal to 0. And so you get 3x is equal to 1, or x is equal to 1/3. So one of our zeros is 1/3. And then we have the x plus 2 gives us the zero, the real zero of negative 2. And so there we go. We found all 4 zeros, which makes sense because we were asked to find the zeros of a 4th degree quadratic. I should have 4 complex zeros, and I had 2 real and 2 strictly complex zeros. And so we've answered the question. Question 4 asks us to find the complex zeros of the polynomial function, and then they want us to write the polynomial in factored form. Looking at this polynomial, it is a 3rd degree polynomial, so that should clue us in that we should have at least one real zero. That is a theorem of this section, but let's think about why that's true. Why does it have to have at least one real zero? Well, looking at this polynomial, it is a polynomial with all real coefficients. So if I have all real coefficients, then if I have any complex zeros, I'm going to have its complex conjugate as one of the other zeros. So those complex conjugates come in pairs, and I can't have a pair make up 3. So even I'm going to at most have 2 complex roots, but I'm going to have at least one real root. Why? What other reasons could you think of that could mean something with an odd degree is going to have at least one real root? Well, when you think about the graph of an odd function, we always say that the end behavior acts like the power function. And so you're looking at that x cubed, the power function is going to go up in one direction and down in one direction. How is it going to do that? Well, it's smooth and continuous, so we know at some point it's going to cross the x-axis. Now, it might cross the x-axis going like this. In this case, we'd have only one real root, and we'd have 2 complex, strictly complex roots. But you also have the option of a different type of graph. So possibly the graph looks like this, where I might have 3 real zeros and 3 complex zeros, but complex and real, no strictly complex zeros. So based on the fact that we know odd functions have to cross the x-axis, that means that odd degree functions will have at least one real zero because it has at least one real x-intercept. That's great news for us as we look at this polynomial and we're trying to write it in factored form. I'm going to go ahead and try to find any rational zeros to see if I can make this a little bit easier. So I'm going to have all the combinations of 1, 5, 17, and 85 divided by 1. So we're going to take these possible rational zeros and we're going to plug them into the function to see what we can, if any of them are factors. And then remember that you can use your calculator to help you plug in all of these numbers into the function. I'm just going to write the answers I got from the calculator in. So we're using the remainder theorem to find out if these are factors. Now Now 1, 5, 17, and 85 and -1 are not factors because they all have remainders when plugged into the function. But we see that -5 would be a real zero because f of -5 is equal to 0. So we know that this is going to be one of our real zeros. Therefore, we should know that we're going to have the factor x minus -5 or x plus 5. And to simplify our polynomial, let's go ahead and do division. Bringing down the first leading coefficient, we get 1. 1 times -5 is -5. Adding together, we get 8. Multiplying times the -5 gives me -40. Adding those together, I get positive 17. Multiplying those together, I get -85. Adding them together, I have 0 as my remainder. So this translates into x plus 5 from the divisor, and then x squared plus 8x plus 17. And so that would be my f of x function written in partially factored form. We do want to factor that out more, and it doesn't look factorable the way that we normally factor it, especially since 17 is prime, but I'm going to go ahead and use the quadratic formula to help us factor this. So having done the quadratic formula, I get my real zero, which is -4 plus I, and my other real zero, which is -4 minus I. And I'm going to take that and to help me write my polynomial in factored form. So I get x plus 5, x minus -4 plus I, and x minus -4 minus I. And let's just rewrite it one more time. This is my polynomial f of x. I'm going to get x plus 5 as my first factor, x plus 4 minus I as my second factor, and x plus 4 plus I as my third factor, making sure to distribute that minus to everything in there. I should have 3 factors. You can see I do, and they're all linear factors because I need as many factors as the degree of the polynomial. This is a third degree polynomial, so I have 3 linear factors. Now this isn't easy work, so you have to practice it. I would suggest that you practice number 4 again, doing it all on your own without referencing this. Then try one of the questions on your homework, doing the same steps. The steps were seeing how many real zeros you might have, coming up with whatever real zeros you can come up with. In this case, we found -5 as a real zero. Dividing your polynomial by that real zero that you found so that you come up with a reduced polynomial, and then using previously learned formulas like the quadratic formula to factor that new polynomial you have so that you can get your complex roots as well. And then making sure that we go back to the question. It says to write it in factored form, so you want to make sure you get 1, 2, and 3 factors, all of them linear in nature. Thank you. Practice this. Come to office hours with questions, and have a good day.